You've probably noticed that many vector spaces look very similar to each other. Just as a couple examples of that, in our R4 looks like this. Let's say A1, B1, C1, D1, right? A column vector with 4 real entries. But a matrix in M22 looks like this. A1, B1, C1, D1, D1. You can see that these look the same. They're just, the entries are just sort of arranged in a different shape. So there's a very nice one-to-one correspondence between these two vector spaces, right? You can just basically reshape any column to get a square, or reshape any square to get a column in reading entries in this particular order. And that sets up a nice one-to-one correspondence between R4 and M22. But that's actually not enough that doesn't really capture what we mean when we say that they're the same, just because there's a one-to-one correspondence between R4 and M22. In fact, there's a one-to-one correspondence between R4 and R, but these vector spaces definitely look different, right? We don't have to have a precise definition for what we mean by look different to have the idea that these two vector spaces shouldn't be regarded as the same. If for no other reason, then they have different dimension. So they definitely can't be the same vector space. So to capture this idea of sameness, it's not enough that there be a one-to-one correspondence. So what do we mean by same, or how can we capture this idea of vector spaces being the same? Well, in addition to having a one-to-one correspondence, it has something to do with the vector operations for each vector space. So in R4, if we add another vector, say A2, B2, C2, D2, right, what you get is A1 plus A2, B1 plus B2, all the way to D1 plus D2, right? You can do the same thing in M22, right? If you add another matrix A1, A2, B2, C2, D2, what you get is a matrix A1 plus A2, and so on, down to D1 plus D2. And what makes this one-to-one correspondence between R4 and M22 special is that the addition we're doing up here in R4 is somehow compatible with the addition we're doing down here in M22, right? If you sort of switch from R4 to, right, you have two ways of getting down here to the lower right. You can either, if you start with two vectors, you can either add them in R4 and then do this one-to-one correspondence, or you can do the one-to-one correspondence to get from R4 to M22 and then add them in M22 to get this very same matrix down here. So this one-to-one correspondence doesn't just give you a one-to-one correspondence. It somehow not only turns vectors into matrices, but also turns addition in R4 into addition in M22. And that's really what makes this special. That's the corresponding thing for scalar multiplication is also true, right? I won't write it down. So that really captures the sense in which these are the same, right? There's a one-to-one correspondence that makes these vector operations compatible. For another example of vector spaces looking the same, we can look at a space of polynomials. So how about the polynomials of degree less than or equal to 2, right? These are polynomials that look like a plus bx plus cx squared. Well, there's a nice one-to-one correspondence between P2 and R3 if you just sort of erase the x's and the pluses. You get a list of 3 numbers, so you can sort of regard that as a vector. Of course, as we saw in the last example, the question isn't just, is there a one-to-one correspondence? The question is, does the one-to-one correspondence turn addition in one vector addition in one vector space into vector addition in the other? So we could do the same sort of thing. Take another polynomial, a2 plus b2x plus c2x squared. Take another vector, so let me put some subscripts on here. Take another vector in R3, a2, b2, c2. Add them. So in P2, the sum is a1 plus a2 plus b1 plus b2 x plus c1 plus c2 x squared. In R3, the sum is a1 plus a2, b1 plus b2, c1 plus c2. And this one-to-one correspondence has turned the sum in P2 into the sum of the same vectors in R3. Right? So we get this same property where we can either do the one-to-one correspondence and then the sum in R3, or we can do the sum in P2 and then the one-to-one correspondence, and we get the same thing either way. Right? So this is this one-to-one correspondence of P2 and R3 has this same sort of nice property that makes these two vector spaces look the same. So let's define exactly what we mean by same. We aren't going to say same, of course, because that word doesn't sound fancy enough. So instead we're going to call this kind of special one-to-one correspondence an isomorphism. Right? Isomorphism, morph is, I think, ancient Greek for form. So an iso means same. So an isomorphism is a function that sort of describes the same form of two vector spaces. That's the idea behind the word anyway. So an isomorphism is a function between two vector spaces that is one-to-one and onto, so it has to be a one-to-one correspondence. And also it respects the vector space structure of both vector spaces. And what we mean by that is if you take two vectors in the domain space V and any real scalar, then f of v1 plus v2 is equal to f of v1 plus f of v2. So, right, this is saying that this addition right here, this is the sum in V, and on the right-hand side, this addition is the sum in W, right? So what we're really saying here is that this function turns the addition in V into the addition in W. And then the corresponding thing for scalar product. So f of the scalar times v1 has to equal the scalar times f of v1. Right? This scalar product is the scalar product in V, and this scalar product here, this is the scalar product in W. So again, we're describing the idea that an isomorphism turns not just vectors from V into vectors in W, but it turns operations in V into operations in W. So the idea with an isomorphism is that if there is an isomorphism between two vector spaces, we can sort of regard the two vector spaces as the same. And we'll make more precise later what we mean by the same, but essentially what's going to happen is any question you can ask or answer, or any calculation you can do in one vector space, you can turn into a question, calculation, or answer in the other vector space using an isomorphism, and you'll always get the same kind of answers. So that is the way in that, that's really the meaning that we're trying to get at when we say that two vector spaces have the same form, isomorphic.